There's plenty of seats up front, so I won't feel too guilty if you're in the back row and can't hear me. All right. I got lots of cough drops ready, so when class is over, or I might just start slurping on them. And when you watch the video back, I'm sure that'll be real annoying. Okay. 1. How many of you have received that evaluation, course evaluation email? Good. Yeah, it should be out by now. This is your friendly reminder. It's the last time I can remind you that the anonymous course evaluation, 4 little questions sent to your official UID email. I'd really appreciate some feedback. I won't know who said what, but I will know the total number of responses. And as I told you before, if 80% or more of the entire class respond, I will give everybody some extra credit as incentive to take a few moments. You have until Sunday, I think, to complete that. Number 2, I'm, as a concerned teacher, that's redundant. I'm getting concerned. I've talked to several people, questions, emails, the TA for this class. And long story short, you guys, this isn't your life. You have lives. You're busy. However, I can tell from looking at who's looked at the answer keys, who's asked me questions, how many people are taking advantage of the following resources. The textbook. I can't cover everything, but I try to. But the book can do it in more depth than we have in class. And just from some of the questions people have asked me, it's word for word in the book, so I know they haven't even looked at it yet. So I encourage that. You have each other. I've had lots of people ask me, oh, well, can't I work with a friend? Well, sure you can if you want to get together. The WebAssign forum, that little chat room we set up, granted, if you don't use it, that's fine. However, if more people used it, that would be an awesome student resource where people would post their confusions and whatnot. Right now there's only ever been 1 post, and that was more just a subject heading. But it's there for you. The teaching assistant herself said that she is not being used much at all, and if you can't remember her where or office hours, it's posted online on my syllabus. It's every Monday through Friday from 2 to 4, if you can make that. If not, you can contact me. We'll set up a time. You have the videos of each of these. There's tutoring services the department and the university offer. My point here is you have resources. I can tell the majority are choosing not to use them. I just want you a friendly reminder so that if you feel like you're struggling and don't know what to do, you have lots of options. All right, today I have some fun. I'm ambitious, and I think I can get through most of this. Because we only have a couple concepts left, and then I wanted to just reiterate them, re-emphasize them, different twist on it with these demonstrations and see how it relates. Okay, we left off Archimedes Principle. I didn't write it down, but we discussed it, and I repeated what it was multiple times right at the end there. It has to do with the buoyant force. Does anybody remember the buoyant force equals what? See if anybody happens to have it in their head already. From your last time notes or the book.
Force of air minus force of in.
Good, that's one way to find buoyant force. Very good. You weigh something in air like us, but then you hop in a pool and you weigh less. You can feel that. That difference is the buoyant force, an actual number for that. Archimedes' principle states it another way. And it was that I tried to show you with an apparatus and some clicker questions. It's equal to the weight of the, that's right, displaced fluid. I say fluid because if it's water, it's water. If it's air, it's air. If it's glycerin, it's glycerin, as long as it can flow. So this works for any fluid. If you had to state Archimedes' principle, that's what it is. It says that the buoyant force acting on something in a fluid is equal to the weight of the displaced fluid. And how does the volume of the displaced fluid compare to the object that's in it? They're equal. What if the object isn't all the way underwater? Would it displace its own volume of water? No. It would displace a part of it. And the weight of that displaced water, which would have less volume, would be the buoyant force. So the more something's underwater, the greater the buoyant force. Now, so you can see something that I think is kind of cool. Weight is mg, right? Now, what's this mass? What's weighing that? I'll put dF for the displaced fluid. It's the amount of fluid displaced. It has a certain mass, and it weighs something. If you rewrite mass in terms of density, mass over volume, then mass is density times volume. Density of what? The object or the fluid, do you think? This came from the mass. Mass of what? The fluid. So this is the density of the fluid and the volume of the displaced fluid. So that is the second formula or guide to your thinking for buoyancy, buoyant force. If you put something in something that's more dense, it'll feel a larger buoyant force. So when you go from fresh water into seawater, which has salt, it's more dense. So for the same object, you move into salt water, like the Great Salt Lakes. Anybody been out there and floated? You feel a lot bigger buoyant force. And that's why. And the other important thing is the volume here is the volume of the displaced fluid, not the object, but how much water is displaced. If the whole object's underwater, it is the volume of the object. They're equal. But if it's only partially submerged, then not all of it. So, we saw that pressure was density times gravity times height. It depended on the density of the fluid also. But it was dependent on the height. Remember, it didn't matter how wide the container is. It could be holding back the entire Atlantic Ocean. But if you're 100 meters down, that determines the pressure. You could be 100 meters down in a big swimming pool, and you'd still feel the same pressure, because it's what's above you. So pressure is depth dependent. Buoyant force doesn't care about how deep you are. It cares about the volume you're displacing. So if you jump in the swimming pool and you're just under the surface, you're displacing the same amount of water as if you were at the bottom of the ocean. Approximately. But you get the idea. At the bottom of a swimming pool, for sure, the volume you're displacing is the same. So the buoyant force on you is the same. Buoyant force is dependent on the volume, not depth. Pressure is dependent on depth, not volume. So let's see why some things float some more. This is what seems to catch a lot of folks up, so I want to do some more probing of you. What two forces are equal? Help him out. It's weight, right? Which is mg. We've done balancing forces before. I hope that makes sense. It's not going up or down, so those two forces are equal. Let's do this guy. And the diet. The diet is like 98% underwater. If I just hold it underwater, who's feeling the larger buoyant force? The diet, because it's floating? What determines buoyant force? The density of the fluid it's in. Well, that's the same for both. Gravity, that's the same for both. Volume of the displaced fluid. The one in the box. If I have this one underwater, they're both displacing the same volume of water, correct? So they're both feeling the same buoyant force. I know some of you are still confused, but does that part make sense? So why is this one floating? Right, it's less dense. So, we'll just use this. If its weight is more than the buoyant force, it sinks. That's the regular pop. It's too heavy for the buoyant force. It's not displacing enough water to create a large enough buoyant force to float it for its weight. But the diet is. The diet has the buoyant force is larger than its weight, so it rises up. Until some of it comes out of the water. What's that do to its buoyant force? I want more people to think. When it comes out of the water, what happens? It displaces a little less volume of water, so its buoyant force is a little less. And what do you think it goes down to? Until they're equal, because they're balanced right now. So, weight does not determine whether something sinks or floats. Buoyant force does not determine whether something sinks or floats. The combination does. Something can be really heavy and still float. A ship. It's which one's bigger, right? Yeah. Again, if this is bigger, it sinks. If that's bigger, it rises up until it displaces less fluid and floats on the surface with some of it out. Yeah.
Was that the same principle I was researching this earlier about if you had like a spoonful, I guess, of a neutron star, if you dropped it and it goes straight through the earth, it's dense, it doesn't matter.
Yeah, neutron stars are very, very dense. Very, very. That means there's more mass and less space. And so, yeah, that would sink in even the Earth, maybe. Yeah. All right. Which one's feeling the larger buoyant force? Which one's displacing more fluid? The buoyant force depends on how much volume of water is displaced. Since the blue is displacing more, it's feeling a larger buoyant force. Now, that should make sense. Which one of these do you think's heavier? I'll give you an idea. This one's hollow plastic, this one's wood. Which one's heavier? The blue. Yet they're both floating. Well, if this one's heavier and it's still floating, there must be a larger buoyant force to balance it. That's why, to achieve that, it has to displace more fluid, because it's heavier. The red one, when I push it under, what happens to the buoyant force? Yeah, it increases. Good. Very good. Okay, clicker time. All right, the session ID number will be coming up shortly. All right, bottom right, you can log in to ResponseWare. Give you a minute to do that. And then there's a couple questions on here I want to ask you. Check your understanding. Raise your hand if you still need the ID number. All right, polling's open. Two tubes, one with fresh water, one with salt water. At the same depth, will one have a greater pressure? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 2/3 of you think B. Good. Pressure is density times gravity times height or depth. If you're at the same depth, they have the same height. But salt water is more dense. That increases the pressure. Salt water is heavier for the same amount of volume. So it's going to weigh more and push down on you more. Salt water would have more pressure. Well, if you were clever, you saw the answer. Oh well, I'm going to poll it anyway. Go. A ship weighs 20,000 newtons out there floating in the ocean. So what's the buoyant force on it? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, you're out of luck. 85% B. Was that because you knew it or you saw my answer? If it's floating, no matter what it's floating in or how much out of the water, if it's floating, it's not going up or down. And so the buoyant force balances its weight. If it weighs 20,000 newtons, the buoyant force must be 20,000 newtons. What if you put more cargo in? What would happen to the ship? More weight, thus more buoyant force. And what would the ship do in the water? And why would it sink? Because it needs to displace a little more volume of water to have that bigger buoyant force. If you put too much weight in the boat, it would keep sinking, displacing more volume, but at some point it'll go under. It can't displace any more volume of water. Thus, its weight's going to win and it'll sink. Plus it'll take on water, which will add on even more weight, and yeah, anyway. Yeah. No. Where was that one? There was one more I liked. This one. Go. A balloon full of air. It's just floating. Just floating, barely. If you push it on the rest of it underneath the water, what will happen? A couple things are going on here. So you could weight this so it's just floating. If you shove it underwater, think about what's going to happen to it and why. More of you have responded than I thought. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 78% say come back to the surface. What happens when you go deeper into water and you get more water on top of you? The pressure does increase on you. If something is not rigid like a balloon, what do you think will happen to the balloon if you go down? Its volume gets smaller. So do our lungs. When we go deeper underwater, the increased pressure from the water above us pushes on us. And it pushes on our lungs and the balloon, which decreases its volume. So let's vote and see if you still want to agree with the same answer, because that still makes sense, or not. Polling open. See if that changes anybody's mind or not. Up until now, we've been thinking about rigid things, but things that can actually give, they will. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, a lot of you changed your mind. The correct answer is sink, which still wasn't the majority. The key to this one, and this was a hard question, if it was just barely floating, that means its density was just less than the density of water it was in. The buoyant force was just enough. So it was displacing just enough volume of water. That one wasn't on purpose. So if you push it down any further, the volume decreases. What's that do to its density? It increases its density if the volume decreases. Now it's more dense and it sinks. Also, it's displacing less fluid, so the buoyant force isn't enough to hold its weight up. And so it would actually sink. A lot of scuba divers don't account for this. They think their buoyancy will just naturally float them back up to the top. If you go down too deep, even on a human, the lungs feel that pressure. And there's less air in you. That changes your density and increases it. And at some point, you don't have enough buoyant force to just naturally float back to the top. And you can try it with a balloon. If you weight it underwater so it's just floating, and you shove it down, you'll see it happen. It'll sink. Any questions?
It's not really a question. I think you should probably rewrite that problem because
Okay.
I thought that you meant that since you said balloon was a helium-filled balloon right there, weighted down barely to float. I thought it was like barely on the surface, and that he was.
Oh, like the water was here?
Yeah, exactly.
Instead.
So that's why.
Okay.
I said it was quite surface. But I mean, I would have said the other one if I knew that.
No, thank you. That's great. I can reword that. Good thing I asked it on the clicker question then, not the test, right? But again, that's a perfect example of if you're not sure where I meant on a task question, ask me. Thank you. Okay, you can put your clickers away. Atmospheric pressure. This chapter should be a lot easier. It goes much faster. You're probably thinking, oh, you finally got to it about gases. But all the principles are the same. Gas is a fluid. So everything we've talked about is true. There's increased pressure with depth, including the air. So what do you expect the pressure to do when you go on top of a mountain? Decrease. If you have less air weighing down on top of you, then the force isn't as great, the pressure isn't as great. But the deeper you go, the increased pressure. And Archimedes' principle holds too. Now we're just dealing with the fluid of air. It's less dense, so the buoyant force isn't as large as when we're in water. But we still displace a volume of air. That air just weighs less, so the buoyant force is less. But this helium balloon, this is full of helium. Helium is less dense than air, so it wants to float. Its volume displaces an equal volume of air because it's completely in the air. If we would weigh that air, how much it weighs, that's the buoyant force on it. And that's what's overcoming its weight. The buoyant force in this case is bigger than the weight, so it wants to go up. The system, with its basket, it still has the same buoyant force, but that's not enough to overcome the system's weight, so it doesn't go up. These are different values for atmospheric pressure. They're all the same thing, just different units, I should say. over 100,000 pascals. Remember, that's force over area. This is kilopascals. You've probably heard 15, technically 14.7 pounds per square inch. That's this one. This weighs 15 pounds. Go. Not real heavy, but it's not light. And if I hold it like this, I'm not feeling 1 atmosphere. But if I hold it like this, that 15 pounds is acting over a square inch. And if you want to try this afterwards with your hand like this, it's not comfortable. Ow. But you can handle this because the area is bigger. That's what you're feeling right now. The amount of air on top of you equates to about 15 pounds on every square inch of your body. So imagine this, on your hand. Now cover your entire body with additional 15-pound posts. That's what you're feeling right now. So next time somebody calls you a wuss, you tell them, no. So why don't you collapse? Why don't you just implode? Yes, we are engineered, our bone structure, that is part of it, but an even bigger factor has to do with the pressure inside us. It's the same pressure inside as outside, so there's no net effect. If you could lower the pressure inside, then there'd be a big pressure difference, wouldn't there? I can demo that one with a volunteer, if somebody's willing. Who'd like to feel that difference? You guys are so fun. Okay. I'm going to ask you to climb inside the bag. It's clean. So get in there, face your friends, get down on your knees. Yeah, and pull it up as high as you can go. All right. You get to hold that inside, and I'll hold the bag. We'll stay safe. Yeah, that works. Yeah, great. Okay. I'm going to pull some air out of the bag. That will decrease the pressure inside, correct? That's in this chapter 2. It's called Boyle's law. If you decrease the pressure, or the volume, the pressure goes down. Anyway. My point here is we're going to make a pressure difference. Atmospheric pressure outside, 14.7 pounds on every square inch of his body. If we could drop the inside to 0, which this won't do, the difference would be 15 pounds on every square inch. This really only, don't worry, we're getting there. Oh, I'll just do it and then I'll talk. Okay. Can you stand up? Can you wave? Thanks. You can free yourself. And those values are at sea level, standard values. We're higher than sea level by about 4,000 or 5,000 feet. So the pressure here is less than that right now. It's about 12.5 pounds per square inch. And this does not pull a perfect vacuum. It probably dropped the pressure 3-4 pounds per square inch. So you felt it, let's say 3 pounds per square inch difference. But you have a lot of square inches, no offense. Remember Pascal's principle? A little difference in pressure over a big area can create enough force he couldn't even stand up or lift his arm. So we only notice pressure when there's a difference. That's what drives our weather, differences in pressure, pushing things around. All because of the weight of our atmosphere. Let's do this one. All right. I have a ball here that doesn't fit in the jar unless I pushed really hard. Okay, you get the idea. I'm going to light this paper, stick it inside, and then see what happens. Get in there. What pushed it in? It wasn't me. Pressure. Which pressure was larger, out here or in there? Out here, pushing it to low pressure. We heated up the air inside. When air gets hot, it expands. When it cools, it took up less space. That dropped the pressure inside briefly. That drop in pressure allowed the greater atmospheric pressure to push the ball in. This is fun with a hard-boiled egg, too, if you want. So I always like to ask, how do you get it back out? Shoot. If I could increase the pressure inside, so I'll blow on it. It's sealed, and I'll try to blow around it. There we go. Yeah. That's a fun one. Here's another good one. You can do this with a pop bottle, but I have glass. I'm going to stick the balloon inside. And there's a hole on this side. If I plug that hole and I try to inflate the balloon, oh, that hurts my head. Sinus congestion. You can't do it because as it tries to inflate, it increases the pressure inside, which is now fighting me. Just remove the cork and allow atmospheric pressure to get inside. Now you can inflate it. But it doesn't stay inflated because the elasticity of the balloon deflates it. But watch this. Let me plug the hole up while it's inflated. Now it's still open to the atmosphere. Atmospheric pressure on this side, but it's atmospheric pressure on this side too. I sealed it. I pushed some air out and dropped it so you can keep it open. If you unplug it, now the elasticity of the balloon wins. You can see the space in there now. But it's still open to the atmosphere. So you can have some fun games with atmospheric pressure. You can even do it, I learned this one in Scouts. There's a hole at the bottom of here, so you know it'll be a lot of pressure and want to squirt out. But the lid's on. I'm going to open the hole. Oh my gosh, nothing shoots out. Why? If you were observant, a little water came out, but that dropped the water level. But it's sealed up here, so that decreased the pressure up here. Atmospheric pressure, the air in the room is holding the water back because it's greater pressure than what's inside. If I loosen the lid a little, I can make it atmospheric pressure here on this side also. And the water can squirt out. Whoop, and make a mess. All right. Tighten it back up. And now you have a camp shower. Lots of holes. You need some water. Just unscrew it a little. Then tighten it back up. I never actually did that on a camp out, but it works. So loosen the lid. And now the depth, the pressure due to the weight of the water pushes it out because the pressure in the air is the same. Close it. This drops a little, increases this volume, which decreased the pressure, less pressure inside now, and the air holds it back. Do you remember this one? Our makeshift barometer. We used it for depth of pressure before, but you can use it as a barometer to measure atmospheric pressure. They're the same height because the same pressure is pushing down on this side as this side. The air is the same. But when you tighten this and seal this off, now if the pressure increases due to the weather, your barometer goes up. And how much did the pressure go up? This height difference, right? You can figure it out. And, oh, look, high pressure front came in. What if the pressure drops? Well, your barometer goes back down. If the pressure in here were to go even further, it would drop below that level. And that's basically how a barometer works. So how much water do you think you could hold up, maximum? This column of water could keep going up, couldn't it? How high could the atmosphere hold up water? Well, here's a straw. And I know nobody wants to do this because I have a cold. And you don't want to touch it. But what I've done is water in here. Tube goes up and back down to here. Atmospheric pressure on this side and this side. So they're at the same height, minus some capillary action. So if I lower the pressure on this side, you know what happens. It goes up. Whoop. You got to make sure the other end's underwater. There we go. So now you can say I suck. But I want to teach you that we can, there's no such thing as suction. So, no, I do not. Because I'm not really sucking. I'm not pulling the water through the tube. Something is pushing it through. What? Pressure due to the air in the atmosphere is pushing down on here. If I lower the pressure on this end by removing air, that drops the pressure over here, and the air in the room pushes down on the surface of the water and forces it up the tube. You can only get so high because we can only lower our pressure so much. But if you kind of do it in spurts, you get a little better. Okay, that's enough. And then you need a drink because you're really dry. Well, what I'm trying to emphasize here is the column of water gets taller and taller. So it's providing more and more pressure in the tube. So I have to decrease the pressure over here more and more and more. And I can only do that so much. What if we put a vacuum pump on here and pumped all the air out of this side? We could drop the pressure on this side to 0. So what would be the difference in pressure? 1 atmosphere of pressure. And that's what these values are. 1 atmosphere can hold up. Sorry. That's what I get for thinking ahead. Yeah, that's right. 1 atmosphere of air can hold up these values. About 30 inches of water, 760 millimeters of mercury. They use that with blood pressure. It could hold up 14.7 pounds of something over a square inch. That's the value. This works out to a straw. No, something's not right. Why did I write that? I must have copied it wrong. That does not seem right. Just forget the water one. That's not right. It should be 10.3 meters. Your book explains this and gives examples of water. What that means is if you go underwater 10.3 meters, you now have on top of you 1 atmosphere's worth of pressure, in addition to atmosphere. So when you dive underwater, you have the atmosphere pushing on you. And if you go 10.3 meters down, you now have a second atmospheric pressure's worth on top of you due to the water. Does that make sense? So if you go another 10.3 meters, you'd have 3 atmospheres of pressure pushing down on you instead of the normal 1 we're used to. So what that means is if you got rid of everything and had a difference of 1 atmosphere, you could only raise water up 10.3 meters. Theoretical maximum. Because you can't lower the pressure any more than that with 1 single pump. Okay, this one. A balloon in a bell jar. I just blew it up. We're going to seal it off like the guy in the bag. And I'm going to remove air on the outside of the balloon. I love how people close their ears. It's inside the jar at least. So, this was what happens to scuba divers that come up too fast. They go down, the pressure's greater on them. So they have to pressurize their air tanks to keep their lungs balanced. So they're under greater pressure. If you come up too quickly, back to less pressure, well, your lungs are under big pressure, like inside the balloon, at atmospheric pressure inside, because that was normal air, sealed. If you now come up and decrease the pressure around you, you expand. People that come up too fast, they don't normally rupture their lungs, but air bubbles in their blood can expand just like this balloon. And if one of those goes to your brain, oops, let the air back in, and it goes back to normal. The pressure's now the same on both sides. But this one's more fun. What's shaving cream mostly made out of? Exactly, air. Trapped in little cells. It's like a bunch of little balloons. So, let's pull the air out. And I'll stop before it gets sucked into the pump, because that's bad. So that would be like a bad case of the bends right there. But again, this is Boyle's law because of a difference in pressure. We've learned that value likes to stay constant if the temperature isn't changing. So if we change one of these, the other compensates. You decrease the pressure, its volume goes up. It's Boyle's law. It's in your textbook, but that's all it means. I got one more to do because I want to help you on some homework. Your book explains it really well. But while I have just this one set up, I want to show you. Then we'll discuss it when we review Monday. We'll finish Bernoulli's Principle Monday, and we'll review everything on liquids and gases, because you have another test on that Wednesday. Your homework is due Sunday. Your course evaluation is due Sunday, closes. We'll review Monday and give you another test Wednesday. But I just want to show you this. I'm going to blow air through this. It's open to atmosphere. Because Bernoulli's principle, everything else still holds, but something else happens when you start moving a fluid, causing a flow. Here, the area gets smaller. So watch what happens to the tubes full of water underneath. The pressure drops here because this came up. There's less pressure pushing the water down, and so it raises up. less pressure in a small area. When the air stops moving, they're all at atmospheric pressure. But where air moves more quickly because it goes through something smaller, or because it gets deflected around something, and that's what I'll show you more of next time, the pressure decreases. Where air is, or a fluid is moving faster, the pressure decreases. Here, it gets crunched in there and has to move faster to get through, drops the pressure, and the water can come up. Have a great weekend.